Hello again. This is Math 2333 coming to you from the College of DuPage. The title of this lecture is Vectors, Operations, and an Application, and I'm reminding you to be an active learner as you watch this video. The term vector is used by scientists to indicate a quantity such as a displacement or velocity or force that has both magnitude and direction. A vector is often represented by an arrow or a directed line segment. The length of the arrow is called the magnitude of the vector, and the arrow points in the direction of the vector. We denote a vector by putting a letter in boldface, or more often, putting an arrow on top of it. For instance, suppose a particle moves along a line segment from point A to point B, corresponding to displacement vector. So it has an initial point A, that's the tail of the arrow, and a terminal point B, which is the tip of the arrow. And we indicate V by writing this, and you can see that A is the blunt end and B is the pointed end. And the vector U, which is equal to CD, has the same length and same direction, even though it's in a different position. That means it's really the same vector. We say they are equivalent or equal as vectors, and we write U is equal to V. There is a zero vector denoted by this. Notice that this is bold, meaning it is a vector. It has length 0. It is the only vector with no specific direction. And here's a picture showing the U and V. They're equivalent vectors. Notice that they are parallel. That means they're pointing in the same direction, and they're equal in magnitude or length. Now we can combine vectors both graphically and algebraically. Here we're talking about graphically doing the vectors. So we can say that if we take vector AB and add it to BC, that is done by placing the tail of AB on top of the point, or it's rather the point, the terminal point of AB on top of the origin of BC, and then connecting the dots where there actually are at the end. So in general, if we start with vectors U and V, we move U so that its tail coincides with the tip of U and define the sum in that way. And this is the definition of vector addition, just as we had it. Now the definition of vector addition also, you can see that it's done here as well, and this also sometimes is called the triangle law, because the length of U plus the length of V has to be more than the length of U plus V. We'll talk about this, calling this the triangle inequality later. And sometimes they talk about this being the parallelogram law, because you see here this is also U as well as this is U, this is V as well as this is V, and so that's the diagonal of the parallel. So this is the graphical addition that we have for vectors. So if we're adding A and B, for example, what would happen is we would say here is A and here is B. So we pick this one up, we put the tail right here, and you see you get A plus B here. And you might notice that that's the same thing as if we added B and A in the different order, but both times we get A plus B, and the vector is the same. It's also possible to multiply a vector by a real number C. And in this case, we call the real number a scalar. That means it is not a vector. That means it has only a magnitude. That's how numbers work. So for instance, if we want to say 2V, that's the same vector as V plus V, and it's the same direction as V, but it's twice as long. So in general, this is it. If C is a scalar and V is a vector, then a scalar multiple CV is a vector whose length is the absolute value of C times the length of V, and whose direction is the same as V if C is greater than or equal to 0, and opposite if C is less than 0. Now that's kind of complicated, and the example might really help you here. If we start with V, 2V is going in the same direction, but it's twice as long. 1/2 V is going in the same direction, but 1/2 as long. This is going in the opposite direction, the negative, and this is multiplying it by 1.5 and going in the opposite direction. The difference is found by u minus v is u plus the negative of v. And you can see that here, if we wanted to say u minus v, we say that u minus v is the vector that you have to add to v to get u. So here if you go v and u minus v, you get u. So that is the geometrical interpretation of the difference of vectors. And here we're supposed to draw a minus 2b, so here's a and here's b. So the first thing we want to do is, here is a, but we're subtracting off 2b, so we go in the direction of b, but twice the opposite direction, and then we connect the tail with the head again. Now, for some purposes, and in fact I would say more often than the other case, we will consider components. So we introduce a coordinate system and treat vectors algebraically. So if we place the initial point of a vector A at the origin of a rectangular coordinate system, then the terminal point of vector A has coordinates parentheses A1, A2, or A1, A2, A3, depending on whether you're in a two-dimensional coordinate system or a three-dimensional coordinate system. So these coordinates are the components of A, and we write A is equal to, and please note that this is A is equal to pointy brackets, A1, comma, A2. And A in three dimensions is pointy bracket, A1, A2, A3. And so we use this pointy bracket notation so we don't confuse them with the ordered pairs. So here are examples of those. And notice that we started this vector at 0, 0, and we're going to refer to that as a standard position in a bit. So the vectors shown in figure 12 are equivalent to 3, 2, that's down here. And you can see that all of these go over 3 and up 2. They have the same slope, so they're all parallel, but notice that the origins happen differently. So we think of all of these geometric representations as representations of the same vector, which is pointy bracket 3, comma 2. But the particular representation where you go from 0 to p, where you start at 0, 0, the origin, to the vector, to the point 3, 2, parentheses 3, comma 2, is called the position vector. Not the standard, it's called the position vector of the point P. Sometimes in some books it's called the standard position. And here are some representations of that. Now in three dimensions, the position vector is found the same, but you notice that if we started somewhere else, like at x, y, z, this is the same vector, and it just goes, the same thing, but this is showing the ordered pairs, but both of these represent the same vector. So given points A being the point, ordered triple x1, y1, z1, and b, x2, y2, z2, then a vector with that representation means that the difference where you go is A, this vector that is this one, is pointy bracket x2 minus x1, y2 minus y1, and z2 minus z1. Okay, so find the vector represented by the direct line segment where we start with this initial point and this terminal point. Well, we just use that formula, we subtract. Notice that sometimes it's a minus times a minus. So we do coordinates, so we take the coordinates of B minus the coordinates of A, and we get this representation. So the answer to this problem would be pointy brackets minus 4, 4, and minus 3. We define the magnitude or length of a vector V is the length of any of its representations, and it's denoted by the symbol. It looks like an absolute value, but I have a vector in there, so that is magnitude of V, or sometimes it's used as a double bar. Using the distance formula to compute the length of a segment, we get the following formulas. If you have a vector A that is pointy bracket A1, A2, it is this, the square root of A2 squared plus A1 squared, square root of all that. That's the magnitude of A, or if you're in three dimensions, it is this. Now these are using the place where you're taking the magnitude of this, which is going from the origin, or 0, 0, 0. So these are formulas you want to commit to memory. And we add vectors algebraically. You just add them component by component. So if we were adding pointy bracket A1, A2, and pointy bracket B1, B2, we would get pointy bracket A1 plus B1 and A2 plus B2. So you add them by components. Similarly, if you're doing scalar multiplication, it's just drawing a bigger but similar triangle. And here is a formula where, so if A is that pointy bracket A1, A2, and B is pointy bracket B1, B2, then this is the sum. And similarly for three-dimensional vectors, we add them component-wise, and this is the way we do scalar multiplication. So here's a problem for you to do. So if A is this, pointy bracket 4, 0, 3, and B is pointy bracket minus 2, 1, 5, I want you to find the magnitude of A and find what these vectors are. A plus B, A minus B, 3B, and 2A plus 5B. Now, I'm going to give you an opportunity to finish this, so you should pause the video. And we'll return and look at the solution in the second part of this. But now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you, and I will see you in part 2.